Okay, well, thanks so much for this invitation, Raimundo. It's been just a pleasure to be here so far. So in this talk, this talk really is intended for folks that know not a lot of fancy math. So please feel free to jump in if you have any questions or comments even. So the goal here, I'll say, is twofold. First, to give a definition of factorization homology in a simplified setting, the first setting that John mentioned. Of these symbols. In the case where, so this will be as a topological space, where X is a pointed topological space, and A is an abelian group. So that's the first goal. It's just to give it a precise definition of these symbols in this case. And the second goal is to show how this construction recovers homology as you know it with coefficients in A. So that's the goal of this and possibly the talk after that. Okay, so A here will just be a fixed abelian group once and for all for this and the next talk. So I'll just jump straight in to defining this symbol, factorization homology. I'll say in words, but I won't write on the board because the words take them less seriously, but I hope it drives your intuition for what I will write on the board. And I think John even mentioned this. What this is could be thought of as the free A module on X. Well, X is a topological space, and so what I mean by a free A module on X there, I expect the output to be another topological space. So defining that topology accounts for some of the subtleties. So it accounts for the subtleties that will occupy the next 10 minutes. So here's the definition. I'll define this topological space first just as a set, and then we'll discuss what the topology is on that set later. So definition. So let, for X, a pointed topological space. So I'll think of X as point inside of X. I will not distinguish notation between X and its pointed version. So for X, a pointed topological space, the set is labeled configurations in X, where the labelings are in A. So it's a set of pairs. First, a finite subset of X. And X is a base space, so for reasons that we'll end up seeing a little later on, a little unmotivated at the moment, I'll say it's a finite subset of X when you remove the base point. Actually, I'm going to mod it. It's a finite subset that contains the base point. Together with a labeling system from S without that base point to A. So an element of this set is a pair. It's a finite subset of X that contains the base point. And a way of assigning to each element, non-base element of that finite subset, some element of A. And before I go on, if X was a topological space, or it was just a discrete topological space, a set, then this would look an awful lot like that intuition we just talked about, the free A module generated by A, or X. So let's put a topology on this now. First off, maybe a picture. So there's X as a base space, and an element in this set are a few dots in X, finitely many, and each dot is labeled by an element of this abelian group, A1, A2, A3, and A4. The topology that I'll talk about momentarily is precisely intended to accommodate movies of pictures like this, where you can watch the points wiggle around and not interact, perhaps. You could also watch two dots move toward each other and collide. When that happens, the topology will add the labels. When 2 points collide, the labels will add. Another kind of move that this topology will accommodate is watching a point slip into the base point and be forgotten. So I am about to give a topology to this set that accommodates those kinds of maneuvers. So toward the topology. A topology. Well, you know, one technique for putting a topology on sets is to find surjective maps from, so here's a technique for putting a topology on a set. Find a surjective map from another topological space to the given one, and then give that target set the quotient topology. So that will be the idea we'll take for putting a topology on this. However, we won't just find one set that maps to this surjectively, or one topological space that maps to it surjectively, but a bunch of them that together map surjectively onto this. And these are explicit. So notice this. So for each k greater than or equal to 0, denote, so I'm going to erase what I just said, actually. So for each finite set equipped with a point, so just an abstract pointed finite set, I'll denote it like this so that I can play around with the base point in the notation. So this is a pointed finite set. Its base point will be indicated by that sub plus. We can denote x upper I plus. By this, I'll mean the collection of maps, base maps, from I plus to x. X is a base space, so this has meaning. And you know, this is just a finite fold product of x. So this is a topological space with the product topology. Now, with this notation, here's a map. It's from something I know to this new thing, namely x to the I plus, which was just talked about, cross a to the I, so the abelian group I many times, that maps to, actually I'm going to put this somewhere where there's more space to write what this map is. X to the I plus cross a to the I maps to this set on which we'll put a topology. And it's given by sending a map, a base map. I'll call it C for configuration. If you
The I is I plus without the base point.
Yes. Thanks. So a point in this product is a base map from I plus to x, which I think of as a configuration of points, not necessarily distinct in x, together with a collection, an I-index collection of elements of this abelian group A, and it carries that to just what you would expect. If this map C was injective into x, then behold, I'm staring at a picture that's exactly of this type. If this map is not injective, for instance, it sends 2 points to 1 point, how do I get a picture that looks like this? Well, I can just sum up the two labels, or the multiple labels that are coinciding at that point. That's the formula I'm about to write down. So this goes to the pair, the finite set, which is the image of I plus. That's a finite set inside of x, together with the map from it without the base point to A that's given by sending some element in there, call it little x, to the sum, which has meaning using the abelian group structure. It has not been used until this moment, of the sum over all the elements in the preimage of x by way of the map C of the labels alpha I. So that's a map. From this set to that set, it's obviously not surjective because I put no bound on the cardinalities of the finite sets on the right-hand side, whereas obviously the cardinalities in the image of this will all be bounded by that of I. Nevertheless, as you vary I over all finite pointed sets, I plus, then what you get is good enough to define a quotient topology, as I'll now describe. So definition of the topology. So we declare a subset V of this labeled configuration set to be open if its inverse image in all of these is open with respect to the topology on this, ultimately given in terms of the product topology on x to the I plus. Let me give this map some notation. I meant to. I'll call it Q sub I. Q kind of like quotient. If Q sub I inverse of V as a subset of this is open for all I. Base finite sets And that defines a topology. So I'll describe, again, the types of continuous movies that are accommodated by this topology. Are there any questions up to this point?
I'm not seeing where you need X to be a pointed space, because there you the configurations removing the base point. I'm not seeing why X has to be defined.
Yeah, so speak up if I'm interpreting the question incorrectly. If you were given a just topological space without a base point, couldn't you still do the same construction? Am I interpreting that correct? Yeah, so that's a good observation. Let me write the answer on the board. So I'll say construction. So I'll say that there's two constructions, and you're picking up on one of them. So I'm going to give two constructions for how to obtain pointed topological spaces from just not necessarily pointed topological spaces. A first construction is, for X, a topological space, we can obtain a pointed topological space just by adding a disjoint base point. Then we get X sub plus. By this, I mean X disjoint union in the so this is a different connected component than that. That's the topology I put on that disjoint union. Now, if you're given a regular old topological space, not necessarily pointed, you could perform this construction on it, and then insert that into this picture. And the effect of that is that you might as well. This is heuristic, but there is no interaction with the base point. And please speak up if this is not satisfying your curiosity. There's another construction provided, so for X locally compact and Hausdorff, there's the opposite kind of thing we could do. Instead of adjoining a disjoint base point, we could adjoin a base point such that you get closer to it as you leave compact subsets of X. That's the one-point compactification. X upper plus, this is the one-point compactification. And this is a different way that, given a topological space satisfying those mild point set conditions, you get a pointed topological space. And both of these are interesting ways of viewing this construction in the unpointed setting. Any questions about that? So an example, stereographic projection. Offers the identification of the one-point compactification of Rn as homeomorphic, and from here on out, I'll just say equal to the n-sphere. I should have said that this I will always regard as a pointed topological space whose special point is the point at infinity. Okay, so picture of a continuous path of a continuous map from the closed interval to this now topological space might be given something like this. So at time 0 of this continuous path, I see finitely many dots, each labeled by elements of the given abelian group. This is at time t equals 0. And let's say at time t equals epsilon, in the very next moment, I can see some of these dots wiggle around ever so slightly. So this dot moved a little forward that way, that one moved a little faster. Let's say that one stayed stationary, and this one started moving toward the base point. I omitted the labels from it. That's an epsilon. At time t equals 1 minus epsilon, let's say it's a similar picture, where this dot is now extremely close to the base point. That one just stayed stationary, and these two dots are extremely close to each other. And then at time t equals 1, I see a single dot remaining, that dot, and no dot over here. That's an example of a continuous path in this topological space, where this now has the label A1 plus A2. That's still labeled by A3, and that label was just forgotten. So the topology that we put on this topological space is such that this picture indicates a continuous map from the closed interval. Okay, so here are some more examples, or some examples. A first example, which is awfully trivial, is that when you insert a base finite set itself, the result is homeomorphic to A to the I. That's one awfully simple example. Here's a more interesting example. And I'm saying that there are examples, but maybe I should say just how this factorization homology is related to other things you might know. In this case, factorization homology, this labeled configuration space, is very simple. In the case where the abelian group is the integers, this offers an interesting map from it to a circle. And I'm going to call it, I'll call it the circle. And I want to view it right now as an abelian group by way of rotations. And I say that so that I can use that structure to write down this map. And it's given like this. Given a finite subset inside of the circle and a labeling system L from that finite subset to the integers, I assign to that this sum, which has meaning because this is an abelian group, of the label at S, which is some integer, times S. That has meaning because every abelian group is a Z module. And this is a sum over the elements of the set. Now, here I'm making use of the fact that I can identify the one-point compactification of the real numbers with the circle itself. And I'm doing that here in such a way that the point corresponds to the identity element in that group. So here, R plus is being identified with circle as in over there, stereographic projection, such that this corresponds to, I'll say 1 in the complex numbers there, the unit. So this map is continuous. This is a continuous map. Now imagine how you try to show this. Certainly the map is defined. To see that it's continuous, one has to inspect the definition of the topology. And it's defined where, so one needs to verify that inverse images of opens are open, but the opens in factorization homology are defined so that their yet further pre-image inside of things like this are open. And that's a pretty simple thing to check. So the fact that this is continuous is not hard to check. And we'll see as a consequence of results later. So this is I'll just name it as a fact right now. And to verify this fact is much more subtle. The fact is that this map is a homotopy equivalence. Induces an isomorphism on pi q. That's the qth homotopy group. For all q. So we'll come back to facts like that. I just wanted to mention it now because here we see this new thing and we're recognizing it as the circle. And if you're in the know, you might see that there's maybe something unsurprising here because the base loop space of the circle is the integers. So another example, and by example I just mean how it's connected to other things of interest. What's that? A homeomorphism? No. And the reason I can just answer it so with such confidence, this has dimension 1, and Lebesgue dimension is a homeomorphism invariant. This has Lebesgue dimension infinite, and you can see it because these finite sets can wiggle around independently for any cardinality of finite set, if that carries meaning to you. Oh, just the covering dimension. Like, you know, so this receives an injection from configuration spaces of arbitrarily many points in R, a topological injection, or an inclusion.
If I take the trivial group,
Okay.
and I forget about the labeling,
Okay.
this symbol of integral is just configurations of points in X.
This is the Ron space.
And if I do the same thing for S1, so 3 points in S1, I would expect it to be S3.
Oh yeah, this is the most fantastic.
Right. And so certainly that's not an isomorphism by 1.
Perfect. Yeah.
Somehow surprises me that adding Z, this is counterintuitive to me.
Oh yeah, yeah. So I'll write that down because it's such a part of the awesomeness of this fact, which again is a consequence of things we'll see later, is this sort of surprise that this very nice, smooth manifold, finite dimensional topological space. This is the first topological space we see in point set topology classes is being identified, at least in the sense of homotopy theory, with this thing, which we see as infinite dimensional, so configurations of k points in R crossed. So when you divide out by a diagonal action of the permutation group, the integers cross k, that includes into this thing. And so this can be very high dimensional. That's a good question. So that's just a comment. Okay, here's another example, just to connect to things that we may have seen. So there's, one could look at Laurent polynomials over the complex numbers. And just remember the zeros and poles with multiplicity. So there's certainly a map into this where I put down here the complex numbers. And so that to make it a base space along the lines of over there, we get this map. And because the zeros and poles with multiplicity does not, this is given by sending a polynomial, or a Laurent polynomial, to its set of zeros and poles. With multiplicity. So that is in particular a finite subset of the complex plane with labels and integers. And this clearly factors through the units in the complex numbers, because the zeros and poles don't notice when you scale a polynomial. And it turns out this, too, is an interesting map. But I just want to point out that there is a map, and this is continuous. So here we saw that there's this interesting thing, or this new thing, and it maps continuously to classical things, and it receives maps, continuous maps from classical things. Okay, so let me name a series of properties that this factorization homology has. Are there any questions? Yes. Huh?
Define a space. What is that space connected?
I mean, huh? Yeah, well, so here's an example where it is not connective, because A, in general, has more than one element. And notice that that's maybe related to the non-connectedness of I sub plus. In this case, the one-point compactification of R is connected, and lo and behold, because of this assertion, this is induces an isomorphism on homotopy groups, in particular zeroth homotopy groups. That means this is connected. And so observation, or not observation, fact, provided let's see, is this right? Is that the connectedness of X, provided X is connected, then this is connected. And I'm going to put an exclamation point there, because that's not obvious, I'll say. Actually, it is obvious. So here's the reason. So if X is connected, then in particular, every point in X, and by connected, I'll say I mean path connected, then every point in X has a path to the base point. So if you start with any labeled configuration, then you can one by one select paths that pull each labeled configuration to that base point. And now that works fine if you're in dimension greater than 1. If you're in dimension 1, you can just do it also more explicitly by hand. So the reason is because given S subset of X labeled by A, then pull each s, comma L of s, so to speak, to the base point. And this can be done because x is connected, path connected. Any other questions? Okay, here's some properties. And these properties will probably occupy the rest of the talk. The properties will get increasingly more complicated, but I think not so complicated until perhaps the last one, which requires the most explanation. So property 0 is that these topological spaces themselves are pointed. Namely, there's the empty configuration and the unique map from the empty set to A. Oh, that was supposed to be, it's the empty set with a disjoint base point, and then the map from the empty set, which is the unique map to A. So this is pointed in a very natural way. The next property is, I'll put it up here, that this is functorial. So we'll call this property the pointed property, and this property the functorial property. And what I mean by that is the following. So for each, part 1 of this is for each based continuous map, from x to y, carrying the base point to the base point, so a pointed one, call it f, and me saying pointed means it sends the base point to the base point. Then this induces a map on factorization homologies. And that goes by this expression. It sends, I guess, s sub plus inside of x, comma, s goes to a by L to the pair. And it's exactly what you would think. To name an element of here is to name a finite subset first, and that's just the image of this finite subset, f of s plus. That sits inside of y. And then is to name a labeling system. And if, for some reason, the given map f does not collapse any part of S, the labeling system then would be identical. But if it were the case that f as a map from S to its image was not injective, then I would just sum up all of the fibers of that map. I'll write that down. Fs plus without the base point maps to A by sending a y to the sum of L of S over all elements S in F inverse of y. And that has meaning, again, using the abelian group structure on A. So each pointed continuous map from x to y induces a map between these factorization homologies. And there are two most notable instances of that, namely coming from these two constructions. So in particular, so if this is just any old continuous map, then that induces a continuous map after you adjoin disjoint base points, which is pointed. S is a finite set. Continuous and pointed. And then the other example is if y to x, if this map is an open embedding, and both x and y are locally compact in Hausdorff between then we get a map the other way between their one-point compactifications. Continuous and pointed. So this, what I'm calling functoriality, it's most interesting, in my opinion, in these two cases. So there's this covariance with respect to regular old topological spaces, unpointed, that you make pointed in that way. And then there's this contravariance with respect to open embeddings, which you make pointed by taking one-point compactifications. Any questions? Let me write down an expression for that map in case it's unfamiliar. It's a wonderful map called a collapse map in some circles, I suppose. It sends x to, I hope you can see this, one of two things. I'm just going to erase things. To either f inverse, if this map is called f inverse of x, if x is in the image, and otherwise it's the base point. That's certainly a formula one can write down. The fact that f inverse of x consists of only one point is because it's an open embedding, in particular injective. The fact that this is continuous is the awesome part. So more on being functorial, and I'll just write this down quickly, is also if you compose two pointed continuous maps, the resulting maps on factorization homologies also compose. So this respects compositions. I'll just write it like that. And also, obviously, it sends the identity map to the identity map. So that's what I mean by this functorial property. As a next property, property 2, I'll call it monoidal. Well, given two topological spaces, you can form their disjoint union. Given two pointed topological spaces, their disjoint union, unfortunately, is not another pointed topological space. For now, there's two equally preferred base points, but you can identify them to get a new pointed topological space. The formation I just outlined is called wedge sum. So for x and y topological spaces, pointed, then we can form their wedge. And by this, it's meant x disjoint union y, where we identify the base point in x with the base point in y. And it's in this sense that we could wonder about how this construction of factorization homology interacts with that. And the answer is simple, which is that it interacts with it by sending wedge sums to products. So here's another property, and I'll call it the continuous property. Which is that if two maps, F and G, between pointed topological spaces are homotopic to each other in a pointed sense, then the resulting maps between these pointed topological spaces are homotopic as well. So if F is homotopic to G as maps from X to Y, then their induced maps, I didn't give it notation, and I'm now regretting that. I guess I'll call it this and that, although, whoops. Then those two maps, the induced maps on factorization homology, are homotopic. So are there any questions about that, namely what homotopic means? So in particular, as a corollary of this, if X and X prime, two pointed topological spaces, are homotopy equivalent, then their factorization homologies are equivalent. If X and Y are homotopy equivalent, then the answers for these factorization homologies will also be homotopy equivalent. So as a special case of that, we see that, for instance, this cross an interval from 0 to 1 is homotopy equivalent to its likewise without that interval. So already this carries this computation, which was immediate from definitions, this identification, in the case of a finite set, to say that on Rn, one with a disjoint base point, factorization homology in the setting I'm talking about in this talk is just A. So that was one instance, and here's another instance. I'll put that line back later. Also, we see that this on Rn sub plus, where we just add a disjoint base point, A is equivalent to just A alone, a feature that factorization homology tends to have in general. Okay, so I'll say one more property and then state another And discussing that other property and its consequences will occupy the next talk. So property, what number am I at? 4. I'll call it a sheaf property. So let U and V be two open subsets of X that together cover X. Then, and suppose that X is locally compact and Hausdorff. Oh, whoops. So then the factorization homology of U intersect. Yeah, I want to do the one-point compactification version. So let me erase the base point. So X is just a topological space with no base point. Suppose X is locally compact and Hausdorff, just exactly so that one-point compactification construction is allowable. Then we have a diagram of this form. I said that open embeddings induce pointed continuous maps the other way, and factorization homology is functorial by what was said as one of the previous properties. And in that way, we get this diagram comprised of factorization homologies and continuous maps among them. And the statement is that this diagram is a pullback diagram. Then this is a pullback diagram. Shall I explain what pullback means? I'm happy to, but I don't want to bore people otherwise. Pullback, yes, no? What?
Something about that property there, the monoidal property.
Sure.
So you have maps from, you're sending a co-product to a product, and you have maps from X into your X wedge Y, from Y into your X wedge Y.
Yeah.
So by your functoriality, by your property 1, you have also maps from, so you have maps from this product on the right-hand side to both of its factors and also from each one of them to that product.
Yeah, you can collapse. There's maps from X wedge Y to X, and likewise to Y. So that induces the map.
That induces both of those maps.
Yeah.
That was my question.
Yep. What's that?
Does it behave nice on this match?
There is an expression. The suspension is so there is an expression in general. The suspension is the easiest to describe, and we'll get there. Yeah. Yeah, that's a good question, and that addressing that will occupy the next lecture. Because, and I'll say, as my second stated goal is to relate this ultimately to homology. And as you know, homology interacts in a very particular way with suspensions. So if indeed there is some relationship between factorization homology over X and over the suspension of X, those should be related if we expect that relationship on homology. So I'll state this next property and not explain it until the next lecture. So this next one is due to Dold and Tom, though phrased slightly differently. So property 5, and this is the hardest, and I'll call this the homotopy sheaf property. Or actually, I just realized I'd rather call it the excision property because of how it lines up with homology later. And it's a lemma due to Dole and Tom, which says this. So let x sub minus, x sub plus, x sub 0 be locally compact Hausdorff topological spaces. Left and right. And say we have topological embeddings from x0 into both of them. Topological embeddings. Then we can form this new topological space, X, which is what we get by gluing XL and XR together, not quite along X0, but along a cylinder for X0. So a schematic picture is this shape, where that's the cylinder. So a slice here is x0, that's x left, that's x right. An example of this, actually I'll talk about these examples later. So the statement then says this. Then this diagram of factorization homologies. X, where I remove, let's say, the left part, and remove the right part. And finally, remove both the left and the right part, resulting in x naught cross the open interval from -1 to 1. One-point compactified. So we get that diagram just from the functoriality of factorization homology, as named in a previous property. And the statement is sort of like this statement, but it's not pullback. Rather, it's homotopy pullback. This is a homotopy pullback diagram. And I'll start the next talk with explaining what homotopy pullback diagram is. Okay, thanks.